Welcome back to Cloud 42, I'm James. Behind me here is my CNC mill. This is a Grizzly G0704 manual mill that I converted to CNC a couple of years ago. When I did the CNC conversion initially, I used NEMA34 motors on all three axes. And as it turns out, while it works, the NEMA34 is a little bit lightweight for the Z-axis and it limits the speed that I can move it. So it is time to upgrade. Last week, I showed you how I made the motor cover for the new NEMA34 motor to protect the electronics and provide a place for the connector. This week, we're going to make a new motor mount, install the motor, install the new driver, and get it all running. As long as we're here at the mill, I'll give you a tour of the CNC conversion. Several of you have asked about that. We'll take a look at the limit switches, the electronics install, and we'll get the speeds and acceleration on the new motor tuned up, get it all running. Okay, for comparison, this is the old motor that I had on the Z-axis of the mill. This is a NEMA34, 570 ounce-inches, about 4 Newton meters of torque. And this is the new motor, which delivers about double that. This is a NEMA34, delivers 1,200 ounce-inches of torque, which is what, 8.25, 8.5 Newton meters, something like that. So roughly double the torque and roughly double the weight. Now the couplers that I'm using here are what are called high parallel misalignment couplers. And I order them from McMaster-Carr, and what you do is you buy the collar that goes onto the shaft. In this case, this might be 8mm, I'm not sure exactly what that is. But you buy the size, you buy these two halves separately in the size that fits whatever you're attaching it to. So this is a 1/2 inch shaft, so I bought a 1/2 inch coupler half, and this is smaller, so I bought a smaller one that fits it, and then you buy these discs that go between them. These ones are acetal, you can also get them in nylon. The acetal ones are more rigid and have higher torque handling capability. Now these fit on actually in contact with zero clearance, maybe even a tiny bit of preload, so you don't end up having, there's zero backlash in the coupler. And because these can slide, the disc can actually run off center, and if the two halves of your coupler as they come together are actually misaligned, this is, more than would be supported, then that disc will actually rotate and move off center and transfer the power even though the shafts are not lined up perfectly. And so that just makes it a lot easier to drill holes and anchor down parts in the mill and line the motors up without having to get out dial indicators and do all kinds of crazy alignment feats. Now to actually mount this onto the mill, there is a motor mount. And again, this is Haas's design. I bought the Haas machine kit. So the way this works is this part bolts down onto the top of the mill column, and then the motor bolts down on top of these spacers. Now, this particular motor plate, when I made it originally, has two sets of holes, one for the NEMA34, one for the NEMA34, and another set of holes for NEMA34. Now, I didn't, in my infinite wisdom, actually bore the holes for the NEMA34 when I made this initially, so I had to take it off the mill and take it someplace else and use another mill to go ahead and put in these additional holes. Since I had to take apart my mill in order to make the part for the mill, you can see the problem. It would have been much smarter to go ahead, since the plate was large enough, to go ahead and put it in for the NEMA34 when I started, but I didn't. The other thing that you'll note about these two motors is that on the NEMA34, the shaft is longer, which means I need more clearance. So I can't just move these spacers out. I actually have to make some longer ones and mount them in these outside positions, then fit this onto the motor, and then we can mount the motor to the mill. So let's go over to the lathe and make some longer spacers. Yeah, I know, this is not the lathe. This is the top of the mill. Before we go and actually make the spacers, I want to take some measurements and be sure that I really have them the right length. From the CAD drawings and all the planning that I've done ahead of time, I'm estimating they need to be about 2 inches 425, but I want to actually mock it up on here with some gauge blocks and find out exactly the length I want, because I don't want to have to make these things twice. So what you're looking at here is the top of the mill column of the G0704 mill with the end of the ball screw sticking out. Now this, as I mentioned earlier, I think, is a Haas machine conversion. So I actually bought the DVD from Haas, aka Daniel Kemp, who worked out originally a CNC conversion for this machine with ball screws. In fact, I've got double nut ball screws on all 3 axes here. And the way this mill was set up originally, there was an Acme lead screw in the column, and then there was a set of bevel gears at the top and a hand crank on the side over here that came out the right-hand side where this green cover is right now. And the Haas machine conversion just gets rid of all of that. And it's got a set of back-to-back angular contact bearings here in the top and a ball screw that comes right through. Now, I'd love to just tear this whole thing down and show you, well, I don't want to tear it down, but I would love to show you all the details here. But again, this is not my design, and these plans are something that Haas sells, and so I want to be respectful of that. And you know, if you're interested in doing a CNC conversion on one of these mills, go check out his stuff on his website. I'll put a link down in the description. And can you do all this stuff yourself, figure it all out, mount the ball screws, design and machine all the parts? Yeah, absolutely. But you know, he's already worked this stuff out, and I decided that it would be you know, good to go ahead and leverage the work that he's done and maybe throw a few bucks his way for the work that he's done for the community. Anyway, that's what I decided to do. You can do whatever you like. The way this works, the mount plate bolts down on the top here around the ball screw, and then the standoffs are here and the motor sits on top. So I'm just going to grab the motor. This is the coupler, the little acetyl coupler plate, and then the motor goes on top of that. And this is heavier than the other one. Now, I'm just going to set that there for right now. It's not really balancing if there's not a good idea. But what I want to do is get some gauge blocks and build up stacks and figure out exactly how many gauge blocks and exactly what the distance is there that'll make this fit properly. Okay, I've been messing with this for a little bit with some different size stacks of blocks, and this is what I came up with. I'd originally guessed this was going to be 2 inches 425. These blocks are 2 inches 420. So within about 5 thou. And that looks just about right to me. There might be a couple thou clearance in the coupler here, and that'll be easy to fix later. Actually, it's 2 420 on the right and 2 419 on the left because of the limited set of gauge blocks that I have. And I think that's going to be exactly right. So now we can go over to the lathe and actually make the spacers 2 inches 420 and expect that all of this is going to fit when we come back and put it together. Okay, I have 4 pieces of stock cut to make the spacers for the motor mount, and I just need to face both ends, face them to length, and then drill and tap 1032 holes. Let's start by just facing off one end. Okay, to face the other end, I'm going to need to be able to control the length, so I'm going to grab a dial indicator here. And I'm also, if I'm going to do these repeatedly, I'm going to have to control the depth in the chuck. And so I'm going to do that with a parallel. Now, I don't like doing this. I need to make a thinner lathe spider so I'll have a good reference in here because I can put the parallel in here and mount the part. But if you do this, sooner or later, you will, and I speak from experience here, forget to take out the parallel and spin up the chuck. And if you're lucky, you won't be standing in the way when this comes flying out. Okay, so let's see where we are on depth right now. Let me actually just take a facing pass and then we'll measure it and see where we are. Okay, we're shooting for 2 inches, 420. See, can we get this in here to measure it? We cannot quite. So it's back to the parallel. Okay, we're 2 inches, 478, which means we need to take 58 thou off. I'm going to go ahead and take 50 and then just measure again and just confirm that we're really where I think we are. Let's see what I mean? That is not going to make the final cut. See where we ended up there? 420. I will take that. Now I need 3 more. Okay, we drill and tap this, 1032. Grab a drill chuck here. Now I don't think I'm going to bother trying to spot this because I'm using a stubby drill here, screw machine length. And I want about 3/4 of an inch here, so I'm just going to go ahead and mark the drill. And let's see how it goes. And the tap. Lots of A9 here, and let's go nice and slow. There we go. Now flip around to the other side and do all of the other parts as well. That's the last one. Now one last quick operation on these. So there's a lead-in chamfer on the inside, but the outside edge is still sharp from the facing. But I have an outside deburring tool in this little Noga set. And a couple of passes. Puts a nice fine bevel on the outside there. Don't want to make a large bevel because I don't want to reduce the sort of torque bearing surface on the end of the spacer. Just want to take the sharp edge off so that they're nicer to handle. Okay, that's it. Okay, I have the spacers attached to the outermost holes here in the motor mount. These are just 1032 screws through it, and I installed those with blue Loctite. That's Loctite 242. The other thing that I did is these were not very pretty, and this is going to be sitting right here at eye level where I'm going to be staring at it for the next few years. So I chucked the spacers back up in the lathe and hit them with some Scotch-Brite just to shine them up a little bit. Now I'm going to screw this down on the top, again using Loctite 242 because I do not want this coming loose. Make sure these are good and tight. That's the last thing I need is a 1200 ounce-inch motor coming loose up here. Okay. I'm just going to turn this around so that I can reach the set screws. Okay, and let's mount the motor. The acetyl plate goes on like that. Motor goes on like so. Okay, more Loctite 242 on the screws. I'm going to get one in here just so that I know the motor's not going anywhere. Now I'm not going to run these all the way down because I'd like this to have just a little bit of play in it, and I also don't want to crimp the connector if I have it, or the coupler if I have it too tight by a thou or two. Actually, that seems to be pretty good. I can probably just cinch this down. I was going to loosen it on the shafts and snug the coupler up, but I think we're fine. The gauge blocks are a really accurate way to measure, so that shouldn't be a surprise. Okay, that's the motor mounted. The coupler is snug, it looks good. We connect up the electronics here. Okay, I think that is ready to run. As long as we're up here, let me show you what I did here for the Z end stop. Disconnect the cable. Now, this is the opening that used to have the crank for the Z-axis. There was a set of bevel gears that went through and drove the Acme screw for the Z column movement. And of course, since I'm now using a stepper motor to direct drive a ball screw in that same space, I no longer need this opening for the crank. So I originally just made a plate to go over it, but ultimately decided this was an excellent place for a Z end stop so that I could put it inside and not have it outside exposed to chips and debris. So this is just a simple little 3D printed part with a little limit switch on it, just a little lever switch. You know, pick these up, these are 99 cents. Connect it up to the connector on the outside, and this is a 5-pin, what's called an aviation plug. Can you see that? Yeah, you can. And what happens is this reaches in there, and I had to 3D model the column and the ball screw, which is in here, and the ball nut and the screws. And what happens is when the column comes up, or when the head comes up, one of the screws on the ball nut just hits this switch. And so that gives me a nice little limit, so I know I'm at the top of the Z-travel. Covers the hole, and it's a nice, neat little package. Let me put this back in. Now I can make the files for this available on Thingiverse. What's not totally clear to me is if every one of these mills has the holes drilled in exactly the same place. This one was actually up here for a mechanical attachment, so I suspect that it'll work out, but you certainly might have to modify it to get the switch into a position if you used a different ball nut than the one that I used. So down here on the front of the mill under this 3D printed housing are the X and the Y limit switches. Just use the same kind of connector to connect them, and I was able to get X limit switches for each side and the Y limit switch that's just on one end all down here into the same housing. Angle's kind of hard to get a driver in here. I haven't had this open in, I don't know, a year or two. Let's see how it looks in here. Actually, not too bad. Let me get a rag and wipe this out. Okay, this has the X and the Y limit switches in it. The X switches are these two switches here, and they're set up to catch these knobs. There's one here on the front of the table. It's adjustable. You can move it left and right in this dovetail. And there's one all the way over here on the other side, which you can't see. And this is set up so that when it's on the front of the mill, those knobs will come in if you reach either end of the X-axis and trigger these switches. Now, the Y limit switch is down here, and it's set up so that when this is sitting on the front here and it comes all the way forward, that switch hits this aluminum part of the motor mount for the Y axis. And this is just the stock motor mount for the Haas conversion, and I just designed this part so that it would hit that when it comes up to the front. Now, this is designed with weep holes on the bottom to allow coolant or any oil or anything that gets in here to escape, so nothing will pool up. And then the connections, at least the bottom part of the connection that would be down near the bottom where anything might pool, is actually sealed in heat shrink. And you can see these outside edges are beveled downwards so that any coolant or anything that happens to get in the end will find its way out. And it looks like I had a bunch of coolant kind of wicked or by capillary action between the 3D printed part and the cast iron, but it looks like it stayed drained. So I can certainly make this part available on Thingiverse as well. Unfortunately, there's a catch. So to mount it, you can see there's some screw holes in the front of this. These threaded holes were already here. This hole and this hole were for the X-axis locks. So they were set screws, or screws with handles on them, that screwed into the gib to lock the X-axis. Unfortunately, they were not drilled very precisely, so they're not actually level. One of them is a little higher than the other. I just modified, again, since I could print, see how the thing's set, and then adjust it. I went ahead and moved the holes just slightly to make it fit cleanly into the correct position. Okay, this is the electronics enclosure for my CNC mill. I built this up out of an 18 by 18 by 6 inch Hammond box. And unlike the box that I did for the speed control for the 3-phase motor on the lathe, I actually put a board in the bottom of this. This is just a piece of 3/4 inch melamine, and I notched it out a little bit up here to get around the ground screw. Now let's start with the power supply. The power supply in here is an 800 watt linear power supply. So it's a big toroidal transformer wired for 110 volt input, and then it's got a bunch of different filters and regulators on the output. I originally started with a switching power supply, but I started chasing problems with missed steps, and I was having issues where if I had all 3 motors going at once, I was missing steps, and in other situations I didn't. And the first thing that I thought was that maybe I was having a problem with the power supply, because in general switching power supplies are not that great for stepper motor loads. Anything that's really spiky, it can mess with the regulation of the supply. They can shut down momentarily. All kinds of bad things can happen. In general, if you've got lots of headroom, they're fine, but if you have any kind of overload condition at all, they're trouble. And so the first thing I did trying to troubleshoot that is I swapped out for this big Antec 800 watt supply. So this supply has multiple outputs from the transformer and multiple output modules that are all independent, all floating. The first is 48 volts DC, and this is unregulated. So there's a couple of big capacitors to filter it, and then and a big bridge rectifier to drive that, and then it just outputs that 48 volts unregulated. Great thing about that is if you have a current spike, all the stepper motors, take off at once and pull a whole bunch of current, you get a little bit of a voltage dip, but it doesn't cut out like a switching supply can. Second module that's in here is a 24 volt unregulated supply, and that is to power this smaller fourth axis driver that I use for a little, I believe it's a NEMA34 that I use for my fourth axis. You've seen that in the video for the hobbed bolts. And then the last module that's in here is a 5 volt regulated output. Is that right? Nope, it's 12 volt regulated output. And I have that going out to drive the breakout board and the limit switches and everything on the side of the opto isolators that's away from the computer. Okay, so that's the power supply. I've got drivers in here for the X, Y, and Z axes, and you can see I've got those positioned just above the intake fan so that they get the most cooling. The cooling air then flows up across the power supply and ultimately exits out through this filtered opening, and there's a filter on the intake there as well. So these are Kelling DSP-based digital stepper drivers. I originally had a set of linear stepper drivers in here, and I was having, again, all kinds of problems with lost steps. And ultimately, after chasing a bunch of other stuff down in here, that was ultimately the problem. I was getting resonance in the motors, which is a problem that's an electromechanical thing that happens with stepper motors. And at certain speeds, they resonate and you can lose steps. And that's what was going on. And switching out to these DSP-based stepper drivers completely solved that problem. It got a lot quieter, everything ran smoother, and the lost steps went away. So those are the drivers. This is just a parallel port breakout board that you can hook directly to the output of a parallel port of a computer, which I also have in here. And that's ultimately what I was doing originally, was just running this off of a parallel port. And this then provides the inputs and the isolation for the limit switches and the outputs to drive the stepper drivers. And this is the computer I'm using. I've just shoved it all in here. And so certainly from a noise standpoint and knowing what I know now, having messed around with the lathe, I would not have expected this to work, but it does. This is an old Mini ITX motherboard, and this is just a low power VIA chipset CPU, 1 gig of memory running Windows XP. And the hard drive is actually underneath the board. There's a 3D printed tray, because of course there is, with a really small SSD that I bought for like 10 bucks. I think it's a 9 gigabyte SSD, which is plenty to boot Windows XP and run Mach 3. And so some power filtering, and this is the power supply for the PC, so that's all crammed in here. One of the other things that I did when I was trying to track down the lost steps is I got rid of the parallel connection from the PC directly to the breakout board, and instead I decided to get a motion controller. And the one that I selected is an Ethernet smooth stepper, and I could not be happier with this thing. It's connected to the PC with this, which is just an Ethernet cable, so it's actually electrically isolated from the PC, and so it's not running off of the PC. Plus, you're not dependent on the PC to come around 40,000 times a second and actually service all the interrupts and drive the pulse trains for the stepper drivers. Instead, it's sending about every quarter second big blocks of data down to the smooth stepper, and then the smooth stepper is actually stepping the motor. It actually provides what looks like a parallel port output to drive the breakout board and drive the stepper drivers at just ungodly speeds. I think this thing can generate pulse trains at something like 4 megahertz. So 40 kilohertz struggles to do it, 4 megahertz. It's just no contest. So that allows me to run, I think I'm running 8-to-1 micro stepping, and this thing is just smooth as silk. I could not be happier with it. The rest of the stuff in here is just power wiring. This is actually a little wall wart power supply that's providing 5 volts to drive the smooth stepper. And then the rest of this is just AC switching. I've got a control panel on the front, I'll show that in a minute, that has power switches and an emergency stop switch, and I've got the push button to turn the PC on and off, and some LEDs to indicate
the presence of all of the supply voltages. But right now, I'm going to replace this driver. This is, I have to get this out and we'll take a look at which model this is and what its maximum current is. If I recall correctly, it's something like around 4 amps DC. And this is the big boy that I bought to replace it. Should fit in exactly the same space, and hopefully I'll be able to use exactly the same connectors. And this is the KL8070D. So this, I believe, is rated at 72 volts DC max at something like 7.1 amps, which is just which is going to be plenty of power to drive that big NEMA34. So let me disconnect all of this. I'm hoping again that I can just pull the connectors out of this, swap in the new driver, and not have to rewire anything. I'm glad it was this driver and not that one back there. Yeah, so this is the KL5056D, which I also highly recommend. I replaced and ultimately sold some linear or some analog stepper drivers, and this is another one of the digital DSPs. So I'm just comparing the pinouts to make sure these really are identical. Okay, I think we're ready to go. This should drop right in. Okay, well, assuming this all works and I didn't miss something important, that was a piece of cake. Probably should wait until after I have powered this thing up once before I say that. Okay, I'm going to switch the power on to the 48 volt supply, and then I'm just going to check the LEDs down here and make sure that it looks at least reasonable. Looks like the others. And it does. It did exactly what the others did. The red light flashed briefly, and now I've got green lights on. So I'm going to go ahead and turn that off. And let me get this buttoned up and we'll take a look at the control panel. And I have to get up off the floor, and yesterday was leg day and I did squats, and I'm feeling it today. This is the control panel that I have on the front of the box. I just have this box hanging on the side of the rolling tool cabinet where I have my monitor and keyboard right here next to the mill. And this is a 3D printed part, and this is actually a dual material 3D print. This is printed in black ABS with white ABS lettering. And so I did this as 2 parts. And so ultimately what's going on here is I laid down the white and then laid down the black around it and printed that up for 2 or 3 layers and then printed the rest of the part. So the lettering here where it says 48 volts, 24 volts, 12 volts, PC and PC, stop, all of this is actually a second color of plastic printed into the part, which is kind of a cool technique. I was still tuning my printer, so the resolution or the clarity of it isn't all perfect. But I've got power down here for the main power supplies. Switch that on. You can see I've got pilot lights for 48, 24, and 12 volt supplies. No pilot light for the 5 volt. But then I also have the switch down here to turn on the PC and the light for that. So the PC is now booting. Let's play with the motor tuning and see if we can get this thing running. Very first thing I want to do is make sure that it's going the correct direction. Now, I wired it up the same as the other motor. The phase A and B plus and minus wires are wired to the same terminals in the connector that the old motor was, but I don't know if that's standardized in the industry or because these motors came from different manufacturers. Let's just make sure. So I'll just tap up quickly and see if it goes up. And it is, it's going up. When I tap down, it goes down. Okay. Run this up. Now this is the speed that I had programmed before. This is 75 inches per minute. And that's just the fastest I could get it to run with the other motor without stalling. Now I've done one thing so far, and that is I did the automatic tuning parameters on the drive. Driver has the connectors on it here, and then it has a series of switches that are used to set the current and the micro-stepping. And switch number 4 in the center is designed to set the current. If it's on, then when the motors are stopped, it runs full current through the coils as a braking current. If you have it set to off, it switches back to half current, which is normally all you need. If the motor's not turning, then there's really no point in running full current through it. Half current will hold it. But that switch serves double duty. Let me look here, make sure you can see this. That switch is also for the automatic motor parameter tuning. So if you flip the switch down and up, and you flip it twice in any direction within 1 second, then the driver will automatically go through its tuning cycle. And I'll save you the trouble. You just go like this, click, click, and then you hear a wee, and that's it. And what it's done is it's run a series of pulses through the motor and measured the feedback and the resonance to figure out the parameters it needs to use to drive its motor current loop so that it can accurately control the current going through the motor. And so that's the only thing that I've done. I don't know how important that is, but I always do it when I put in a driver that has that feature. You just go click, click, it goes neat, 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 and then you're done. So let's try increasing the speed on this thing and see just how fast we can go. So here in Mach 3, go to Config, Motor Tuning, select the Z-axis, and right now it's set to 75 inches a minute. Acceleration is 4 inches per second per second. So let me change that 75. Let's take it up to 100, which was kind of my target that I wanted to run. See how that works. That seems all right. Let's see how much faster we can go. Let's go to 120. Whoops. Cancel. I have to select the right axis. Motor tuning, Z-axis. Let's try 120. That seems all right. Z-axis, 135. That seems all right, but you'll notice there's a long ramp up and ramp down. And that's that 4 inches per second acceleration. Let's go ahead and figure out a top speed before we go any further. Okay, that's 135. Let's try 150. That seems okay. How much faster can we go? Actually, let's not go any faster than that 150. Let's play around with the acceleration. So right now that's set to 4. Let's go ahead and step that up to 8. So this should accelerate twice as fast. And in fact it does. Let me ref this off of the home switch so that it'll know where the end of the axis is. As this is going faster and faster, I don't want to crash it. Okay, this is 150 inches per minute. Up. And there, we just missed some steps. Okay, let me ref that again. Okay, so it can almost do 150. I'm going to pull that back to, say, 125. Okay, I'm happy with that. Let's see if we can accelerate faster. Okay, so that is 8 inches per second. Let's try 16. Just keep doubling it. That's pretty good. Let's double it again. 32. Okay, 32 inches per second up to 125 inches per minute. That's very nice. And that feels to me almost instantaneous. I don't think there's any point in going faster than that. I think that is a huge improvement. Now, the reason we couldn't go a ton faster is because this motor actually has higher inductance. And the inductance of the motor, as the RPMs and as the step frequency goes up, the inductance causes difficulty getting the current to rise rapidly in the motor coil. And so the torque falls off as the motor speed goes up. And so in general, you want more current to get more torque, but in order to overcome the higher inductance of a higher inductance winding on the motor, you have to have more voltage. And since I didn't upgrade the power supply, I didn't go to like a 72 volt supply, the top speed is not going to be a ton more, but we've got a lot more torque. And that's why we're able, instead of 4 inches per second acceleration, to go all the way up to 32, and maybe more, but I'm not going to push it. And so as far as lift moves Z-lift moves during machining, that is going to be a ton quicker. While we're at it, let's go ahead and turn up the other motors as well. I think I've got room to go on those. So they're running at 100 inches per minute. So like that. And they're still at 8. Let's go for broke. Let's set that to 150 inches per minute. And again, we'll only use that for rapids. And let's set it to the same 32 inches per second. Set the y-axis to the same thing, 150 and 32. Okay, see what that's like. Oh, that's awesome. How about all at once? Okay, I think this is going to be great. Where we ended up is 150 inches a minute on X and Y, and 125 inches a minute on Z. All of those are way faster than we had before. And setting the acceleration all the way up to 32 inches per second is going to take a ton of time out of the non-cutting machining operations. Rapids back during an adaptive clearing, and any kind of a Z-lift to go over a part, or if I was just lazy and didn't extend the keep down to keep the head down during milling. The other thing that I'm going to be doing soon is I'm going to try out some vertical shaping or broaching to try to cut some keyways for the diamond grinder, and we will continue working on that probably next week. In the meantime, if you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.